Welcome to the Explainer. Have you ever actually stopped to think about how a single click of your mouse crosses our entirely fragmented globe in mere milliseconds? Honestly, it feels a bit like magic, but it's actually an incredibly meticulously designed system of algorithms. Today, we're decoding the unsung hero of global communication, path vector routing protocols.
Okay, let's dive into this. The fundamental problem early network engineers had to solve was just massive. How does data cross the globe without getting permanently lost? I mean, with billions of devices out there, data could literally bounce around forever. Without a highly sophisticated navigation system, we just have endless loops and totally crashed networks.
Here is our roadmap for demystifying the invisible mechanics that keep the global internet functioning. We're going to cover 1. The internet's ultimate GPS. 2. How path vector works. 3. Rules of the road. 4. Stopping the endless loop. And finally, 5. BGP, the global backbone.
Section 1. The Internet's ultimate GPS. Let's see what we're dealing with here. Path vector routing protocols are essentially a specific type of routing algorithm designed to determine the absolute best path for data to travel. But here is the crucial distinction. It considers both the number of hops and the explicit sequence of routers. It doesn't just know the general direction. It maintains information about the entire path, the complete itinerary, to a destination network.
This distinction changes everything. Think of it like a road trip. Older methods, like distance vector and link state protocols, they act like a basic GPS that just tells you, hey, your destination is 5 towns away. It only counts the hops on the highway. Path vector, on the other hand, is like a hyper-advanced itinerary. It knows the exact names of the states you'll drive through and the exact sequence of stops. It maps out the whole journey.
Section 2. How path vector works. Let's look under the hood. To really understand the mechanism here, we have to look at the landscape. The internet is made up of autonomous systems, or AS for short. These are independent, connected networks. Think of an autonomous system exactly like a country on a map. Just like crossing international borders on that road trip we talked about, data travels through different, independently managed territories, and this is what we call inter-domain routing. Now, what's really interesting about this slide is how a path vector table maps a destination network directly to its precise sequence of routers. On one side, we have the ultimate destination, say Network A. On the other, the precise path. To reach Network A, data must jump from Autonomous System 1 to 2 and finally to 4. Every destination is mapped directly to its exact sequence of hops.
Section 3. Rules of the road. Because, there have to be rules.
The internet isn't a free-for-all. It's governed by strict, customizable routing rules. Path vector protocols don't just rely on distance, they use policy-based routing. Network administrators can build rules based on overall network policies, personal preferences, performance metrics, the actual length of the AS path, or prefix lengths. It's not always about the shortest physical path. Sometimes it's about forcing data down the most secure or preferred pathway.
So, what happens when a router sees multiple valid paths to the exact same destination? Well, it runs a highly systematic algorithm to pick the absolute best route. Step 1, it checks the AS path length, basically which route crosses fewer systems. Step 2, it evaluates the origin type. And Step 3, it applies those local preferences we just talked about. It aggressively filters its options until it finds the perfect path. Section 4. Stopping the endless loop. This is where things get critical. The biggest threat to a network is a data pocket getting doomed to travel endlessly in a loop. Luckily, this protocol acts as the ultimate safeguard. Because it tracks the exact sequence of systems, the AS path attribute functions almost like a passport getting stamped at border crossings. As a route announcement travels the internet, every system it visits stamps its name on the list. If a router receives a route and sees its own stamp already on there, it instantly knows it's driving in a circle, drops the route, and boom, kills the loop. Section 5. BGP, the global backbone. Time to meet the star of the show. Enter the real-world hero of this story, the Border Gateway Protocol, or BGP. It is the prime example of a path vector protocol exchanging routing information between different autonomous systems globally. When we talk about exchanging data between wildly different globally distributed networks, we are talking about BGP. It is the literal glue holding the modern internet together today. So the crucial point is, managing a system this complex comes with a major reality check: convergence time.
Because path vector protocols analyze incredibly explicit, intricate path data across massive networks, it simply takes longer for all the global routers to agree on new paths after a major outage compared to, say, link state protocols. It's the required technical trade-off for having a highly detailed, loop-free map of the globe.
Every single time you refresh a web page, BGP is silently negotiating global treaties between autonomous systems, preventing endless data loops and dynamically mapping the perfect journey for your data in fractions of a second. It is an awe-inspiring piece of global routing infrastructure. But it makes you wonder, with the internet growing exponentially every single day, what happens when someone accidentally misconfigures this global map and routes a massive chunk of the world's traffic into a total dead end? Thanks for joining me for this explainer, and keep questioning the incredible systems that power our world.